All right, so yesterday we used the feature in Desmos, and if we put in the data, we could fit a sine curve to that data using this regression formula right down here. All right, so today we're going to do the same thing, but now you've got to come up with the data yourself. All right, so if we take a look at this, we've got the height of the axle is 20 meters tall. So on our drawing right here, your axle, this is your axle. So this is 20 meters. Okay, the diameter of the wheel is 30 meters. Okay, so if that's 30 meters, then you know that this distance, this length is 15, and this length is 15. Yep. So the height above the ground right there is going to be 5. Okay, so we already know when we graph this, the lowest that this graph will go will be 5. And what's the highest? No? 35, right. So the max, as we're filling this chart in down here, the lowest, when we're at a minimum, the lowest is going to be a 5. And when we're at the highest point, it's going to be 35. All right, so it says if a person, and it says the clock turns clockwise, or the Ferris wheel turns clockwise, so it's going this direction. All right, so if somebody gets on down here, all right, it'll say if a person gets on the wheel at the very bottom, how high off the ground will they be? Well, we already answered that. Okay, they're going to be 5 meters above the ground. Okay, high off the ground will they be at the top of the wheel? Well, we answered that as well, 35 meters. And then how high off the ground will they be halfway down the wheel? So that would be when they are either this location or this location. Then what's their height going to be? 20. All right. So what it turns out is 20 is the midline. All right. And 35 is the max and 5 is the min. Yeah. Yeah. B and D. Well, halfway up the wheel would be right here. Because you're measuring how far you are from the ground. So it's 15 to this point, and then 5 more, so it's 20. How high are the ground? Halfway up the wheel. Oh. No, that was supposed to, I put it in the wrong spot. That was supposed to be 5, and then halfway up. So if we started here, we'll call this point A. This would be halfway up. That's point B. That would be 20. Yeah. Then at the top, 35. We'll call that C. And then back here, call that D. We're back to 20. Okay, now we're going to model this with a sine curve. Right? So when we model sine, it's going to look something like this. And we know that the high value on this the max is 35. The midline would be at 20, and then the low point is going to be at 5. And for sine, it goes, our pattern goes midline, max, midline, min, midline. So when we're filling out our chart here, our heights are going to go 20, 35, back to 20, down to 5. Oh, nope. That's wrong. That is wrong. Because we're actually going to start at 5. Okay. Okay. So I'm not going to write that out, because we're actually, when we start this graph, guys, this is a normal sine graph, but we're not starting at 0, and we're not starting at 20 feet. We're actually starting at 5 feet. So that's 5, 20, 35. We're starting here, then going to 20, then going to 35, then back to 20, then back to 5. Get rid of that. So this graph would actually look like this. Go ahead and erase that one, and let's sketch this one. 1, then we got 5, 20, 35. Okay, so when we start, we're at 5, and we're going clockwise. So that's point A, and then we go to point B, which is 20 feet above the ground. Then we go to point C, which is 35 feet. Then we go to point D, which is 20 again. And then we're back down to 5. Okay, so your sine curve got shifted. Okay, there's a normal sine curve right there. But to get it to match this situation, we had to slide it to the right, match the graph of the data. So the amount we had to move that is C. To get that to match up, we had to move it C places to the right. Just like that. All right. So you're told that it takes 6 minutes for a full rotation. Complete the table below. Note, you must convert 6 minutes into seconds. All right, so 6 minutes times 60 seconds is going to give us 360 seconds. Okay, so this is 360 seconds. Okay, and then what I'm going to do, that's my period. So our period is 360. All right, and then what I'm going to count by, I'm going to divide that into 4 parts like we did when we graph these guys. 90. All right, so this first red dot, that's 0 seconds. I'm at 5 meters. Then my next dot is going to be 90 seconds, and I'm at 20 meters. And my next one is 180 seconds, and I'm at 35 meters. Okay, then 270 seconds, back at 20. Then 360 seconds, 5. 540 seconds, 20. And looks like we got one more here. Or no, that's 450. And then 540, we would be back up to 540, 35. All right, now that allows you to set in the chart. Okay, so this is 5, right? Then 20, 35, 5, 20, 35. All right, now in a minute, we're going to put these into Desmos, and we're going to get a graph. Desmos is going to give us a graph that fits this data. But before we do that, we're going to predict what some of the values are going to be here before we let the calculator do it. All right, so go back to your, right here, the previous page, and find the amplitude. So using that formula, and using that data right here, what would our amplitude equal? And then calculate what the vertical shift would be. Okay, so looking at this data here, Corbin, what's my high and low data y coordinate? Yep. So there's my low, there's my high. Okay, so now I can get my amplitude, which is just, I'm going to just subtract those two and divide by 2. So 35 minus 5 divided by 2 is 15. So when we graph this in a moment, we should get 15. Okay, and now the vertical shift, yes. Oh, so to find the amplitude is halfway between the highest and the lowest point right here. So we're just taking the high point, the low point, and then we're dividing it by 2, and that's how tall these curves are here. Yep, because the amplitude is measured from the midline. Okay? And then to get the midline, you take these, the high and the low, you add them and you cut it in half, and that gives you where this line is. Okay? That's your midline, okay, which is the same as the vertical shift. So in our case here, we would have 35 plus 5 divided by 2, and that's going to be 20. So A is 15, D is 20. The midline is the same as the vertical shift. Yep, exactly. Whatever the height of the axle is, that is going to be your vertical shift. All right. Then we had to get B. B was the frequency. Okay, and to get B, we use the formula for the period of sine. The period of sine equals 2 pi divided by B. All right. So we're gonna, if we know the period, we can put something in for the period, and then we can solve this for the letter B. All right. So a period is how long does it take until the data repeats? Well, I got 5, 20, 35, 20, 5. Okay. Or another way you can get it, if you look right here, the period is the time it takes the data to repeat. Take the horizontal distance between maximum points as your period. So look at 2 maxes and how far apart are they? So here's 1 max. Here's the other max. All right, so I'm going to take the distance. This is the x, this is the y. I'm going to subtract 180 from 540. But it also tells me what it is right here. This is the period. 6 minutes until you're back to where you started. 6 minutes or 360 seconds. Or the other way to do it is go high point to high point and subtract them. Okay, so I could do 5, yeah, it's the same thing. 540 minus 180. How I did what?
Like, I literally look at 540 and 180 and like.
Yeah.
on my consult.
Yeah. 360. But you really didn't need to do that because this tells you it right here.
Right.
Yeah, it's time it takes to go around once. All right, now that's not B, that's just the period. So now what you're going to do is you're going to solve this for B. Okay, so the 540 and the 180, those were the X coordinates for the two maxes. Max, max, and then I subtract the two X's. I don't subtract the maxes. All right, so I'm going to multiply both sides by B. These B's cancel, and I get 360 times B equals 2 pi. Now divide by 360. Right? And this is equal to 2 goes into 360, 180, pi divided by 180. So that's the frequency. Now, when we do it on Desmos, it's not going to be written like that. It's going to be written as a decimal. So I'm going to convert that to a decimal so we can compare it. Okay, so let me load up a calculator. I got pi divided by 180. Enter. Okay, so when the Desmos does it, we should get a decimal pretty close to this. So I'm going to say 0.017. The 4 would say leave the 7 alone. So 0.017. All right, so we have our, let's see, we got our A value, 15, our D value, 20, and now our B value, is pi over 180, which is about 0.017. Okay, now the C value, that's the phase shift. All right, so let's go down to this here. All right, to determine the phase shift, you're going to use the period of the data, which is 360, and you're going to divide it into 4 sub-intervals of equal length. All right. So when I do C here, let's C, this is the phase shift. Okay, so the first thing said, take the period and divide it into 4 parts. So the period is 360 divided by 4. That's equal to 90. All right, so here are my 4 intervals. From 0 to 90 is an interval. So I go from 0 to 90. Then the next interval is going to be from 90 seconds to 180. Then it's going to go from 180 to 270. And 270 to 360. That's one period. Okay, now follow along up here. Corbin, yeah, watch this, what we're doing. So you understand what you're doing. Okay, so I took that and I divided it into 4 parts. Just did this. Divide the period into 4 subintervals of equal length. Okay, determine the x-coordinate for the maximum of a sine function. All right, so a normal sine, okay, for normal sine starts at the midline, then it goes to its max, then it goes back to the midline. Oh, wait a minute, sine goes mid, max, mid, okay, and then, mid, max, mid, min, mid, okay, so it's mid, max, min, okay, so min, and then this next section would be a max, even though we don't have an interval for that. All right, now go up to the chart here, and where does yours start? Look at the data now. Let's do it like this, guys. I hope you can erase this. Sorry. Okay. When I divide this into 4, this will be 0, 90, 180, 270, 360. All right. That's what a normal sine does. It goes mid, max, mid, min, mid. So this is going to go mid. Make sure I had max there, that was wrong. Mid, max, mid, min, mid. All right, now what does your data do? Ferris wheel. Where does it start? It starts at its minimum. This one goes min, mid, max, mid, min, max. So the data goes, let's see, minimum, okay, then it goes to its max. Well, it goes to its min. Oh, shoot. Okay. So min, mid, max, mid, minimum, middle, max, middle, minimum. Okay, these right here. So what would I have to do to the normal sine curve so that it would match up with the Ferris wheel? How would I have to slide those values? See, I want this to match up with this. That's what this is telling you right here. It says, determine the x coordinate for the maximum of the sine function and the x coordinate of the maximum in the data, and then use this to determine the value of c. Okay, so this is the x coordinate for the maximum of a normal sine. Okay, and this is the x coordinate for the maximum in your data. So what would you have to do to get both of these to say max? What would I have to do to this function, to the normal, to get this to shift over so that's above this one? How many seconds do I have to shift it over? Okay, let me write it like this. This, I'd have to shift it over how far? 90 seconds. Okay, so the max for a normal sine that occurs at 90 seconds. Okay, our data, our Ferris wheel, its max occurs at 180 seconds. So I've got to take the sine graph and I've got to add 90 to it. That's going to be my phase shift. 90 seconds plus my phase shift to get 180. That's going to be seconds. So basically, if I just took this whole if I took that and I just shifted it over 90 seconds, now the maxes and the mins would match up. That's the phase shift. Now the two patterns would match up. Okay, so that's what we were trying to figure out here. Does that make sense? Now you see that? Okay. So that's going to be C when the calculator does it for us. So what we just did is we just did it by hand. All right, so by hand, our equation would look like, this is 90 seconds. All right, so our A value was 15. sine. Okay, our B value was pi over 180. So I'm just going to write it as pi over 180 for now. X. I had to go 90 seconds to the right. So this is going to be minus 90. And my vertical shift was 20. And we just came up with the equation. Yeah. Yeah, can you just see this one thing? If you can hold on a second. Okay, now to get this version of it, you can write it two different ways. To get this version, all you do is you take this and you multiply it through. Right, distribute it. So this would be pi over 180 x. This is still 15 minus pi over 180 times 90, which is pi over 2, plus 20. Pi over 80, 90 is pi over 80, which is pi over 2. Okay. So both of these work. Okay. Now, when you do it on Desmos, it's not going to be pi over 180 and pi over 2. Those are going to be decimals. So this is going to turn out to be a decimal, 0.017, and this is a decimal, like 1.57. So that way you'll know it's the same thing. All right, so now let's let Desmos do the work. And then we'll compare it to what we got by hand. Really, the hardest thing to calculate on these is to get the phase shift, is understanding how the phase shift works. All right, so open up any Desmos file. Okay, so open up a Desmos, Corbin. And guys, if you save it, if you create a Desmos account, they're free. You can save it, and then next time on the next problem, all you got to do is just change the numbers. All right, so I click plus, add a table, and I'm going to put in my data from my from that chart. Okay. The 0, 5. So X's are the times. So this just goes 0, 90, 180, 270, 60, 50, 540. And from our chart, our heights, 20, 25, 20. All right, and now we type in the regression equation. You guys ready? Okay, y1, and then the tilde sign, which is right up by the 1 key on your keyboard. So I go shift, squiggle, and then it's A. And then you can just type in the word sign, S-I-N, parentheses, B, parentheses, oops, parentheses, X1 minus C. Now it tells you got to close it, close 2 parentheses, and then plus D. Got to really zoom out to see it, but there it is. There's my graph. Then each one of these dots are the coordinates of what you put in. And if you look at it, there's your equation. So we got, let's put that on here now. Okay, so right down here, we can fill those numbers in. Okay, the R squared was 1. That means it's a perfect fit. All right. A, we got 15, like we said. C was 90, like we said. B was 0.017, which we know is pi over 180. And D was 20. Now, if you wanted it to look like this one, you just go back to Desmos. You can do it a couple of ways. You can retype it, or you can just get rid of the parentheses. Come on, Desmos. So watch what happens if I just get rid of these parentheses. It's now going to be in the other format. Delete. And there it is. That's the other format. I just got rid of the parentheses. That's the same thing as distributing. Okay, so then this guy was 15. This now was 1.57, which is pi over 2. B was 0.017, which was pi over 180. And D was 20. Which is what we predicted. So either one of these equations predicts your height at any time on that Ferris wheel. Plug in your time, this will give you your height. Okay, we're just about out of time, so we'll stop there. And then this assignment, we're going to do it Monday in class. Mhm. Alt, Alt, P, Alt,